We do have scheduled one of our reviews so far is tomorrow night, and then we will schedule a second review probably either on Wednesday or Thursday. Okay, and so I will post an announcement for the time and the place for that review session. Okay? All right, so I don't have a clicker today, but what I figured we would do is, first off, I'm just going to give you, it's not really a review, but it's just a list of the chapters that we've gone through. Just kind of a, think back to where we've been. And then we're going to finish the synthesis problems that we had at the end of the chapter that were on the on chapter 25's notes, and I'm sure you all thought about those over the weekend before coming in. And then I have some kind of spectroscopy problems that we can work out. Okay? Or if you guys have some general questions, I can try to answer those as well. So here's just our list. So there's been a lot of chapters, and I just wanted to highlight, kind of some of the things that we've been through quickly. So, of course, we started out with all of our spectroscopy and our structure determination. And there will be some problems. One problem on the written portion and some problems on the multiple choice about spectroscopy. Okay? For both of those exams, you'll have the tables, so that reminds me I have to upload the tables for the online one for them to have for you. We then talked about radical reactions, and so you should know the radical reactions, the steps of the radical reactions, right? And then those important reactions like the halogenation, or like on the first exam we had the addition of HBr to an alkene and with peroxide, and you should know how to draw out some of those important mechanisms. We then talked about resonance, and we went through a lot of different resonance examples. Then we talked about reactions of dienes. So remember, we had the Diels-Alder reaction. We had the addition of say, HBr, HCl to dienes, where we could generate either kinetic or thermodynamic products, right? So you should know about that. Of course, I'm going to go through this list and tell you that you're supposed to know about everything, but I'm just pointing out a few things. So then we carried on with resonance, and we talked about the chemistry of benzene. So aromatic compounds, what does it take? The type of resonance structures that we can draw, the electrophilic substitution reactions, right? Activating and deactivating groups, and ortho-para and meta-directing groups, and all of that kind of stuff. And then we started into this huge list of, look at how many here, all of these chapters all had to do with carbonyl chemistry. Okay, we started out with just acids, carboxylic acids, and so acidity of those groups. We fit that into relative acidities of a wide variety of organic functional groups, right? Alcohols, carboxylic acids, phenols. We've added in amines, and all of these kind of groups. Then we talked about, we had this chapter on intro to carbonyl chemistry here, where we primarily looked at the reaction of carbonyl groups with strong nucleophiles like Grignards and hydrides and things like that. Then we looked at aldehydes and ketones with weaker nucleophiles, so we made imines and enamines and acetals and hemiacetals and all of that kind of chemistry. And so I think particularly important are some of those mechanisms that have the acid catalyzed mechanisms, like we had on the exam, the hemiacetal and acetal formation, which is very similar to the mechanisms on the next chapter for the carboxylic acid derivatives, like the Fischer esterification or the ester hydrolysis. All of these acid catalyzed reactions, remember, can only go through intermediates that either are neutral or have positive charges. Okay? Basic mechanisms either are neutral or have minus charges. So then we went through all these acyl substitution reactions. We should know how to convert those from one to the other. And then the last two chapters on carbonyl chemistry all had to do with reactions at the alpha position. So making enolates and using those enolates as nucleophiles, either doing substitution reactions or in chapter 25, reacting an enolate with another carbonyl, okay, to do the condensation reactions, the aldol reaction or the Claisen reaction in those. All right, so we finished up this whole thing on amines, and so we looked at the acid-base chemistry of amines. We learned a new way to alkylate them, the reductive alkylation, and then we did the chemistry of the diazonium salts, which is more benzene chemistry. Okay, so that is a quick rundown over the semester. For each of these chapters, if you've never looked there, there is a page of what I called learning objectives. These are the same ones that are on each of the, the slides that I give you every week. But as another way to review them, you could go and look through those and look at the topics and say, oh, check, I remember how to do that, and oh, I don't even remember that thing. I better look into it or something like that. Another good way, to study is to go back over the old exams. We have both the computer versions are available to redo. The written parts you can download and rework. All the keys are available now. I know it's a lot. All right, any questions? Okay, then. What about synthesis, then? We had two more problems, well, two more benzene-related problems that we're going to try to make from benzene. Okay, so over on one side, we're going to have benzene over here. And we want to make that orthobromophenol. So take just a second, see if you can come up with a general strategy. All right, well, the only way we can put on a phenol, we only have one way to do that right now, right? And what did that involve? That diazonium salt, right? So this essentially has to come from this diazonium salt, right? And that is going to come from an amine, right? From an aniline. And that's going to eventually come from a nitro group. All right, so kind of the question is then where along this series of functional group changes do we put the bromine on? On first?
Yeah, because if you add the OH, it's going to be a strong activated group.
Yeah, we could put it on first. We'll have to do a separation here, right? So we have a hard time actually controlling only ortho, but we could put it on first. If we put the bromine on, right, and we just use Br2 and iron bromide, right? And because bromine, what type of directing does it have? Ortho para director. We could then do a nitration, and what we would get would be a mixture of ortho and para, right, plus this, and then we'd have to separate these. Okay, so we'd end up having to kind of throw away some of our product, but sometimes we just got to do that. Okay, so then we want to go from the nitro group to the aniline, right? So we have to reduce that. We can just use palladium on carbon and H2 if we want. And then we get NH2 and bromine. And then we'll have to go down to the diazonium salt. And we used NaNO2 and HCl at 0 degrees. And we get to this. And then what do we use to convert that diazonium salt into the phenol? Just water. All right, we could do it the other way around though as well. We could put the nitro group on first and reduce it to the aniline and then brominate because it's also an ortho para director, but we wouldn't need to have the catalyst because that's such an active group. Another interesting way that I was just thinking about, let's see, it would probably add too many steps, but sometimes you can do something like this. Let's say we get to the phenol, so some steps getting to here. And then, let's say, then we put a nitro group on it. We get ortho and para. We're going to take the para one. And then we brominate. And so now we have our ortho para director, but the para position is locked, so it can only go ortho to the phenol. And then we go through, reducing the nitro group, making the diazonium salt, and just removing that group. So there are sometimes, this would probably make it kind of a lengthy synthesis, but it would be a way to make it more selective. So we don't have to do that separate. Well, we'd still have to do, I guess, the separation where the para-nitro group is. So this we would go through the diazonium and then we get rid of that. Yeah, question?
Just as a reminder, what are the reagents we need to add to make the benzene a phenol?
Well, we just did that, right? So So to make the phenol, we had to go through the diazonium salt here, and then we added water. Yeah?
Is there another way we can form the phenols? Like, could we just like get the benzene ring halogenated and then do like some sort of like substitution reaction with like an OH group?
Well, maybe. Well, what we would need, remember we had a nucleophilic aromatic substitution reaction. So what we would need would be to have a halogen at that position, but we also need like a nitro group or some electron withdrawing group to do the substitution reaction, nucleophilic one. In fact, there's another way to do it, but we didn't cover it in this class. That in the other textbook, what it does is it actually goes from, you can take like this. I'm sure you guys don't want to hear about any chemistry that isn't going to be on our stuff. And you can take a ketone like this, and you can do an oxidation reaction. It's called the Baeyer-Villiger oxidation. And it'll oxidize a ketone to an ester. It'll insert an oxygen. And for an aromatic one like this, it would insert the oxygen in between the ketone and the benzene ring to make an ester. And then you can hydrolyze or reduce the ester to give the phenol. But we unfortunately didn't have the time to go through all that chemistry. All right, so these are a couple of options for that one. So what about the bottom compound? This is actually an example that was in the book. And I guess they just wanted to use the chemistry we just learned, but I think there's a lot speedier way to do it than what they show it in the book.
Did you just brominate and then do a Friedel-Crafts acylation?
Brominate and then a Friedel-Crafts acylation, and then we have to chop it down to the aldehyde, though. My idea was to do the Friedel-Crafts alkylation first, because then we can book kind of a big group, like an isopropyl or something, and then do the bromination, because then it'll direct it all para. And then we could do the benzylic oxidation to cleave off the alkyl group to the carboxylic acid, which we could then just, manipulate over to the aldehyde. So this is what my idea was. So we start out with the Friedel-Crafts alkylation. And I'm just going to use kind of a big group because I want to direct the bromination to be para rather than ortho. It is an ortho-para director. So we should mostly get this. So we have Br2 and FeBr3. And then we could use potassium permanganate, right, to do the benzylic oxidation. Goes to the carboxylic acid to here. Okay, and so then we have to get the carboxylic acid converted to the aldehyde. All right, so how would we do that? No, sodium borohydride won't react with a carboxylic acid. Remember, it only reduces ketones and aldehydes. Dival will reduce an ester to an aldehyde. No, not that either. Well, I think there's several ways to do it, but each one takes 2 steps. Okay, so we could reduce it to the alcohol with lithium aluminum hydride. 1 lithium aluminum hydride, hydride, followed by water. And then we could use PCC to oxidize it up to the aldehyde.
So,
Yeah.
Could you SOCl2 and then lithium aluminum tetroxide?
Yeah, exactly. So that's one of the other ones. If we convert it, good. If we convert it to the acid chloride, we can use its tri-tert-butoxy aluminum hydride. So it's this specialized reagent for reducing acyl chlorides, acid chlorides to aldehydes. So that's another way. What's a third way we could do it? Yeah.
So you can convert the carboxylic acid to an acyl chloride, and then the acyl chloride into an aldehyde.
Yeah, that's what the last one we went over. What's the third one? Yeah.
have we talked about like if we could convert the carboxylic acid to an ester group? And then
No, we could do that too. We could convert the carboxylic acid to an acid chloride, and then we could use dibal to reduce it to directly to the aldehyde.
Do you mean ester?
The ester to the aldehyde. Yeah, whatever I said. You know what I meant. Yeah.
Can you write the acyl chloride?
No, there's not enough room. Okay, so I'm going to have to go backwards like this. Thionyl chloride, okay, would make the acid chloride like this. All right, and then we can use its lithium, and it has an H and an aluminum, and this is going to be tight here. It has 3 tert butoxide groups. So it's a tert butyl with an oxygen in between, and that will go to the aldehyde. Okay, so in the text, they want to go through the diazonium salt. Okay, so another way to do that is to, what they did is brominate it, then go to the nitro group, then to the aniline, to the diazonium salt, and then remember that with the diazonium salt you can add copper cyanide. And so then it goes to a nitrile, and then you can reduce that with dibal to the aldehyde. All right, yeah?
Couldn't you also, from the diazonium ion, couldn't you also hydrate it, make it into an alcohol, then use PCC to make it into aldehyde?
Yeah, it's not a hydration. That's kind of what we did here. Lithium aluminum hydride. So a reduction would go to the primary alcohol here, and then PCC.
But even from like the alcohol, if you use like the diazonium ion,
Mm-hmm.
it'd be like the last one, but instead of like doing it from
Up there?
it'd be para, and then use the para to become an aldehyde with PCC.
Well, yeah, but we can't go, if we use that chemistry up there to put the alcohol on, there's no carbon in between, right? So we can't make the aldehyde from the phenol, really, because we have to add the carbon. You know, I guess the other way, you know, carboxylic acids like this, if we didn't have this other bromine, or if we did it in a different order, we can, you know, make it Grignard and reactive with carbon dioxide and that kind of thing too, to put a carboxylic acid onto the ring. All right? So I like these problems when there's lots of different possibilities, right? I think it's good. I like to see all the different ideas. Okay, so let's do another process, not aromatic chemistry. Or would you like to just do the spectroscopy instead? This? Okay. All right, so we're starting with an alkane, right? So what kind of reaction do we have to use to derivatize our alkane so we can actually do something? We have two reactions of alkanes. We can burn it, but it's probably not going to go to that product. Yeah, so we can halogenate it, right? So what do we use to just put a bromine on there? Br2, and usually not peroxide, but either light or heat. Okay, so H nu. Okay, remember in this one, what's the first step of a radical reaction? The initiation step. So in the halogenation, the initiation is just the homolytic cleavage of the bromine bond. Okay? All right, and so where does the bromine go? What position? The more substituted, right? And we use the bromination here rather than a chlorination because bromination, remember, is so much more selective for the most highly substituted position. All right, so now if we look at our product, we can see our starting material right here. All right, so we have to do something. We have to add another carbon and a nitrogen to extend that chain, right? And we have to get reactivity out at essentially one of the methyl groups for where we're at. So yeah, the only way really to do that very easily is to do an elimination step here, right? I think pretty much any strong base will cause an E2 elimination because it's a tertiary alkyl halide. We're not going to get an SN2 substitution, right? So it would need to do elimination. Okay, so we get our double bond, and so now we need to do a reaction out on the end. We could do a hydroboration oxidation, which would put an alcohol out there, right? An anti-Markovnikov addition of water. And so just be careful when you're doing these kind of problems. I saw on the synthesis last time a fair number of you who would miscount the number of carbons and things like that, right? And do a reaction like this, but then draw this as the product or something. Oops, that's not a very good H, but so make sure you keep track of the number of carbons. All right, so if we did that, how are we going to add the rest of this stuff here? You could do, well, that would extend move our double bond out one position. I'm thinking that maybe a better way to go here is we could go for the alcohol, but it may be better to just go through a halide, right? So what if we use HBr, and here's where we can use peroxide. Remember, this mechanism was on our first exam. So we put a bromine here, so then we can do more easily do a substitution reaction. So what kind of a substitution could we do to add a carbon and maybe even the nitrogen at the same time? We could use cyanide, right? So if we use cyanide, that does SN2, and it goes to here. All right? What then so essentially now we at least have extended what we have out to this point. Right? But we need to go, for example, from this nitrile to an amine. We could go to an aldehyde. Yeah, here, I'm going to show you my way first. Okay, we can use lithium aluminum hydride. Followed by water. And that's going to go to here. Right? And then we could just add the acid chloride. Like this. To that amine to get the amide. All right. We could get to that amine in different ways, though. We could. It was suggested that if we add, say, dibal, we could go to this aldehyde. And we can't really go directly up to the amide, but we could go this way, and we have a way to just add one nitrogen on here. Or so we could add ammonia along with sodium cyanoborohydride. Okay, so that was the reductive alkylation. And so it forms like an imine, and then it reduces it. And would it go to the primary amine? All right. Any other ideas? No? All right. Well, that's all the synthesis I thought of. So let's jump over. What do we got? 10 minutes left. Yeah?
2 days ago in lecture, we were talking about the microreaction and whether or not we can predict if it's going to move on.
Oh, yeah. I was going to look that up for you, wasn't I?
Yeah. I guess at this point, it's more important for me to know how you want us to approach that on the exam.
Right. I think I would not, so the question is, if we're looking at a Michael reaction versus this Robinson annulate, whether it's going to continue all the way through the Robinson annulation, I think as far as predicting a product, I wouldn't ask you to make that choice. If anything, I'm not saying I'm going to do this, but I could ask you to, say, draw a mechanism for like the Robinson or something like that, right? But I wouldn't necessarily make you predict if it was going to go all the way or not.
Okay, and as far as synthesis goes, would it be appropriate to use the microreaction and assume it doesn't go on to the Robinson annulation?
Yeah, I think so.
Okay.
Yeah. All right, any other questions? All right, let's, I have more than we're going to use here. I'm going to go to the last one that I have here. I did make a couple of problems. Yeah.
Before we move on to this, could I ask you a quick question?
Okay, and this one I actually give a molecular formula. All right, so here's the molecular formula. Let's first figure out how many sites of unsaturation there are in this molecule. Just one? Okay, so remember how we do that? We take the number of carbons, we subtract half the number of hydrogens, but in this case we're going to treat the bromine like a hydrogen, okay, because it essentially has the same bonding characteristics. It can make one bond. And so we're going to subtract from that 16 halves. We would add half the number of nitrogens, but there are no nitrogens, and then we add 1. So 8 minus 8 plus 1, we have 1 site of unsaturation. All right? So do we see any evidence for a site of unsaturation in the IR spectrum? Yeah, so there's a carbonyl stretch right there. All right, it's 1736. All right, we see some CH stretches. And these will all be on sp3 hybridized carbons, right? Because they're less than 3,000. Okay? Let's just start. Just have some NMR for this one. Huh?
I thought you were going to give us that. We thought that was it.
That was it? Just the IR and you have to come up with a structure? No, I'm not that evil. Well, maybe I will be then. All right, so here we have a proton NMR, and we have a C13 NMR. This is a solvent right there. So do we see conformation of the carbonyl? Yes, right here. Right? So this is the carbonyl. Can we tell what kind of a carbonyl it likely is? Hmm? No, it doesn't need to be connected to bromine. But if the carbonyl shift is usually below 190, then it means it's an ester. Okay? Could be an amide too, but we don't have any nitrogens. And so this chemical shift at 173 or something like that suggests that it's an ester. If it was a ketone or an aldehyde, it would be at usually 190 if it had conjugation, or 200 or above. Okay, so we can kind of separate those types of functional groups. Okay, so what do we see in the proton NMR? So maybe it's just start out looking at the integrations. So they all these ones except for the last one look the same, right? So how many do you think they're worth? Probably 2, right? So 2, 2, 2, 2, 2, 2, and 3. Okay? So does that add up to all of the hydrogens we need? It does? Okay, that's good. So then, what else can we pick up? If we see this methyl group as a triplet, what does that have to have next to it? A CH2. Which of the CH2s do you think would be next to a methyl group? Okay, this one, right, has to be next to a methyl group. Why? Because it's a quartet, right? Because a quartet is next to a methyl group. Okay, so that is a CH2, CH3 group. What about the chemical shift of the CH2 group at almost 4 parts per million? What do you think it's attached to? It has to be an electronegative atom. We have 2 choices. Probably that oxygen right there, right? What's the other electronegative atom that we have? The bromine, but if we put a bromine on there, then all we have is bromoethane, and that's not really our whole molecule, right? So here's our oxygen. That's part of the ester. And then the rest of it, right, we have CH2, 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 right? We have no methyl groups, and so it just has to be a chain with a bromine on the end. All right, so I'm going to draw it this other way around. Here's our ethyl, the ester, 1, 2, 3. How many do we have? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Bromine. All right, so we can see the 2 CH2s that are on the ends, because those are triplets, because they only have a CH2 next to it. Yeah?
Can you explain how you got the integration values?
Oh, sure. So the integration, remember, what we do is we just measure the height from the top to the bottom of this, right? And so what I would notice is that that height is the same as this one, right? Is the same. We can just go across and we see all of these are the same until we get to the last one, and that's just a little bit higher. And what we're kind of estimating is that if we take half of this other one and stack it on top, then we get 3. So it's a 2 to 3 ratio. Okay? It could be that these are all, 3 and then, or 4 and to 6 or something, but putting 2s and then 3 on the end add up to the number of hydrogens that we need. Okay? So just the last thing, the 2 on the ends are both going to be triplets, right? Because they only have a CH2 next to it. Probably the one next to bromine is going to be more downfield, right? It's more electronegative. The one that's upfield here is going to be next to the carbonyl. Notice that in the middle, these CH2s are just all kind of coupled to each other. And once we get buried in the middle of the chain, they don't always look as perfect as we might think. Okay, so they can look a little shaggy in there. Okay, but it's just each one in the middle is coupling to 2 CH2s. All right, so it's been real. It's been fun. Good luck on the final. Yeah, see ya.